Greetings, most excellent chemical engineering students. I've got a tutorial for you today on how to design an absorber. We'll get the equilibrium data from the VLE behavior of the liquid components, in this case methanol and water. Here is the problem statement. 100 moles per second of a gas consisting of 1 mole percent methanol in air is contacted with pure water in a single equilibrium stage. Enough water is used to absorb 90 mole percent of the methanol. The stage operates at 10 degrees C and 5 atmospheres. Determine the flow rate and composition of each stream. Now, we need to make certain assumptions. The first assumption is that only methanol distributes between the phases. Air does not dissolve into the water, and water does not evaporate into the air. We also assume that the vapor and liquid achieve equilibrium. The system is isothermal and isobaric so that the temperature and pressure do not change. And the gas and liquid flow rates are essentially constant because such a small amount of methanol is being transferred that does not significantly affect the gas and liquid flow rates. The first step is to draw a process flow diagram. We're going to be feeding 100 moles of a gas, and so I'll say here that G is equal to 100. I'll leave off the units for simplicity. And the composition of that gas is 1% methanol. So I'll write Y is equal to 0.01. That's 1% in mole fraction. We will contact that with water, and I don't know the flow rate of water, so I'll just write L. The composition I'm going to assume is 0, so I'll write X equals 0. And the process specification is that 90% of the methanol is removed from the gas stream. So I'll write PS is equal to 90%. The absorber operates at T equals 10 degrees C, and the pressure is 5 atmospheres. For absorption, generally you want to operate at lower temperatures and higher pressures so that the equilibrium favors the solute going from the gas to the liquid. To round out the process flow diagram, I'll label the unknown composition in the liquid leaving the stage here, and give the X out, for instance, and I'll have Y out up here. I will not relabel the gas flow rate because one of my assumptions was that G and L are not appreciably changed by the transfer of this methanol. The next step is to conduct a degree of freedom analysis. Is there enough information to solve for the unknowns in this problem? So let's look at the unknowns first. They are the liquid flow rate, water, the composition of the liquid leaving, and the composition of the gas leaving. If I look at the equations we have available, we have a methanol mole balance. There's no mole balance for the water or the air because we're assuming that they do not change phase. There's the methanol equilibrium, and there's also the process specification. the 90% removal. So it appears that there is enough information to solve this problem. Since we have 0 degrees of freedom, we can just write down the equations and solve. So for the methanol mole balance, we have, here I'll identify it first, we have the methanol coming in, which is G times Y in. That was the gas flow rate was 100 and Yn was the 0.01. And we have any methanol coming in with the liquid. Well, I'll just write that here as L times Xn. Now that will equal the methanol leaving, which would be G times Y out and L times X out. Remember, we're assuming that G and L are effectively unchanged because it's a small amount of material that's being transferred. Methanol equilibrium is simply a modified Raoult's law. It would be like this. Y times P is equal to gamma, an activity coefficient, times the vapor pressure, times the liquid phase composition. More about that in a second. We also have the process specification, 90% removal, and that is that G, the gas flow rate, times the difference between Y in and Y out divided by what comes in, G times Y in, times 100 to make it a percentage, is equal to 90. And the G's, of course, cancel out. Now, if I don't have the activity coefficient or don't even know what an activity coefficient is, how would I solve this problem? I can use regular VLE data for the methanol water system to determine the partial pressure of methane as a function of X, and that'll give me P sub M. And then Y is just equal to the partial pressure over the total pressure. Let me show you how to do that. I used the process simulator ChemCAD to find the vapor-liquid equilibrium for methanol water, but instead of 1 atmosphere constant pressure like we have done in the past, it will be for constant temperature. And you see here I have pressure, liquid phase composition, mole fraction, and vapor phase mole fraction at 10 degrees C, which I use for absorption, and at 30 degrees C, which I'll use for stripping examples. This is just a selection of the data. It actually goes beyond 0.05 all the way to mole fraction of 1. This is the PXY diagram for this system at 10 degrees C. Here I've got the pressure, total pressure in millimeters of mercury, and on the x-axis I have the mole fractions in the liquid phase and the vapor phase. This is the liquid phase, this is the vapor phase. Now this pressure is due to the vapor pressure of both the water and the methanol. And the scale here is for methanol, the lighter component. So this is 0 mole fraction methanol, 100% water. And over here it's 100% methanol, 0% water. So the vapor pressure of water at 10 degrees C is around 10 millimeters of mercury, and the vapor pressure of methanol at 10 degrees C is about 55 millimeters of mercury. We can calculate the partial pressure of the methanol from this data. For example, if we have a composition of 0.3 in the liquid phase, then the pressure should be, and this is for both the methanol and the water, something like around 32 millimeters of mercury. And the mole fraction of methanol in the vapor phase is over here at, say, 0.77. Therefore, the partial pressure of methanol is the pressure here, 32, times the mole fraction in the vapor phase, 0.77. Here is the XY diagram for the methanol and water at 10 degrees C. It's just a different way of presenting the data that you saw on the last slide. For instance, here at a composition in the liquid at 0.3, the vapor phase composition is around 0.77, as we saw on the PXY diagram. Now, to use these relationships in these graphs, we'll have to fit the lines to a polynomial equation. The previous slide, the PXY diagram for the liquid phase, was well fitted with a 6th-order polynomial equation. Unfortunately, that was not a good fit for this XY data. So instead, what I did is I broke up this graph into different sections from 0 to 0.1, 0.1 to 0.2, and 0.2 all the way up to 1. And those were well fitted with actually lower polynomial equations. After selecting a polynomial trend line for the graph, the data is presented in this form, that whatever's on the y-axis is equal to a constant times the quantity on the x-axis to the 6th power, and then on down to g, which is just a constant. And so I've written those here for the pressure as a function of the liquid phase composition. That's from the PXY diagram. And then from the XY diagram, I have y as a function of x for the 3 different sections that I described. And for the first two, a simple 3rd-order polynomial was sufficient to give nearly a r-squared value of 1. And for the last one, it required a 4th-order polynomial. Now, what I do is calculate, based on whatever is on the liquid phase composition, I calculate the vapor phase composition using all 3 different equations. And I'll use a logical statement in my Excel spreadsheet to select which one of these to use for the vapor phase mole fraction. Here are the calculations that you can find on the accompanying spreadsheet, Methanol Absorber. The equilibrium stage here has a temperature of 10 degrees C and 3,800 millimeters of mercury, which is 5 atmospheres. The green values are specified. So here we have the gas flow rate, 100 moles per second, the gas composition, 0.01 mole fraction of methanol, and the liquid phase composition coming in, which is 0, pure water. Guessed values, which are in brown, are shown here. We'll just guess that the Y value coming out is 0.005 or 0.5%. The guessed value for liquid phase composition is 2%. And the liquid phase flow rate, water flow rate, is 50 moles per second. The objectives, shown in this kind of goldish color, are the three equations that we will set equal to 0 in Solver. Everything in those equations would move to one side so that it should equal 0 when solved. So we have the methanol mole balance, an equation for the equilibrium, and the percent removed, which was a process specification. Finally, the calculated values are all based on whatever is in this cell for the liquid phase composition. So, using the polynomial equations, we have that the total pressure exerted by the methanol and water together at this composition, 2% methanol and the liquid phase, is equal to about 12 millimeters of mercury. The equation used to calculate Y was also based on this mole fraction in the liquid phase, and a logical statement in this cell determines which equation will be used to calculate Y. This mole fraction is not the same as the mole fraction in the gas leaving the absorber. It's the fraction of this 11.84 that is due to the methanol. So if we have 2% methanol in the liquid phase, we actually have 23% of this total pressure here is due to the methanol. So if we multiply this mole fraction by this total pressure, we get the partial pressure of methanol in the gas phase. So the equilibrium then equation becomes that the partial pressure of methanol calculated from this VLE data should be equal to the mole fraction in the gas phase times the total pressure in the gas phase. In other words, PM is equal to Y, and this Y is the gas phase mole fraction, times the total pressure. So this partial pressure is this value. This mole fraction in the gas phase is this value, and the total pressure here of the gas phase is this value. Now, if you have to stop for a minute and think about that as an equilibrium relationship, go ahead. It took me a little while to come up with this myself. Here I've pressed Solver, and Solver changed this value, and this value to make my objective functions here equal 0, or in this case, the percent removed to be 90. And so what we have is it took a liquid flow rate of 32.5 moles per second to effect a reduction of the methanol in the gas phase of 90%. That 90% of the methanol in the liquid phase flow then results in this composition in the liquid phase. Now the hard part is done, and the fun part begins. Can you guess what would happen if we reduce the pressure here? Remember that for absorption, a higher pressure gives you a better separation, or you need to use less liquid flow rate. So if we cut this in half, for instance, then we would expect that the liquid flow rate required for 90% removal would actually increase. Why don't you open up the Methanol Absorber spreadsheet and give that a try and play with the various variables, keeping in mind that you can't arbitrarily change the temperature, because when you do, those equations used for the pressure here and the mole fraction here would be different. You'd have to use different PXY data. But you can change other variables. You can change the pressure. You can change the liquid flow rate. You could change the amount removed and see how that affects the overall operation of this absorber. One of the major assumptions we made in this solution was that the air and the water do not transfer phases. Well, air is not very soluble, so I wouldn't expect a lot of it to wind up in the liquid, but water can definitely evaporate into the gas phase. There's not going to be that much here at 10 degrees C, but if you operate, for instance, a stripper, which operates at a higher temperature, you will get a significant amount of water going into the gas phase.